So we've seen how to use the parsing library in an earlier video. Now we're going to see how we actually define that library. So the library that I've used today is quite small. It has a bunch of functions which you've seen and one or two that you haven't seen but which are used internally but could be useful in general. So this is by no means a fully fledged parsing library. This is just a simple toy version. But there are realistic parsing libraries as part of the standard Haskell libraries which have more or less the same kind of structure as this very simple parser. So the module itself is exporting a bunch of functions and one type, the parser type. An interesting thing to note is that when you export a type in this way, it exports only the type and not the constructors of the type. If you want to export the constructors of the type as well, you can either list them all or you can just write ... to mean all of them. But what that means is that the actual representation of a parser internally is hidden from the users, just like the representation of I/O is hidden from the users. You don't get to actually see what's inside the parser. The only way you can work with parsers is to build them using these building blocks and run them using the parse function. But now I'll have to actually show you what the representation of the parser is. And it's not too complicated. So I've imported a bunch of things that I'm going to find useful. Data.char, functions on characters, data.maybe, you might need some of those. I've also done what I mentioned, or I mentioned in another video, just some standard boilerplate in order that I don't have to think about applicatives and functors. I'm just going to focus on the monad part of this library. So you may remember that we had the type of a parser that we used was just a type synonym, a shorthand. A parser for a thing is a function from strings to maybe a thing and a string. And in order to turn this into a monad, I can't use a type synonym. I need a real type. So I'm going to do the smallest step I can to turn this into a real new type. And that is to add just one constructor to wrap around it. So I've introduced a new type called parser. So this is not being used anymore. It's very similar to what we had before. A parser for A is, well, it always starts with this constructor P and then it contains a function of the obvious kind. A function from strings to maybe a thing and a string. And then in fact all that the parse function does is that it takes a parser, and every parser looks like this, gets the function out from inside the parser and applies the function to the string. So the parse function, you give it a parser, that's the first argument, and a string, that's the second argument, and it maybe gives you a thing and a string. And how does it do that? It applies the function p to s. And in fact, if you run hlint on this, it will tell you just to write it like this. Parsing of p of this thing is just p. But you may find it, for the moment, more intuitive to remember that this, of course, p is a function. So when you apply it to a string, it will apply the function p to a string. Okay, so we're going to start by building some very simple parsers, and in fact they're so simple they might seem rather pointless. But they're pointless until we start using them with other functions to combine together to build interesting parsers. So the first parser I'm going to build is a parser that never succeeds, a useless parser. What does it mean to fail when you're parsing? It means you give nothing. So this is a parser for anything you like, but it will never actually succeed. So what is it? Well, every parser for A has a structure. It's a constructor P containing a function. That function takes a string, and in the case of the failure parser, it returns nothing. We can already run this parser. Of course, it's not terribly interesting, but we can parse using the failure parser on any string we like. But it doesn't matter what string we give it, we'll always get nothing, even if the string is empty, of course. Okay, so if that's one extreme, the parser that always fails, what's the other extreme? That would be a parser that always succeeds. So what does that look like? Well, that's the success parser. And I've noticed instead of putting brackets around here, I've just put a dollar instead. It's the same thing. Okay, so what does the success parser do? Well, if you're always going to succeed, you need a value to succeed on. So I'm going to parse with the success parser, and I'm going to produce the number 42, and it doesn't matter what string that I apply it to, it will always succeed. So if I apply it to that string, it will succeed, giving me the value 42, and actually it won't have used up any of the string at all. So the rest of the string will be the whole string. Okay, so how is success defined? Well, it always succeeds with whatever value you've given it. So if you give it a value a, it's a parser which, when the function is given a string, it succeeds. In other words, it produces a just of a and the whole string. So that's a function that always succeeds, again, on its own, rather uninteresting, but when used in combination with other things, will be very interesting. Okay, let's take something which does something slightly more than those parsers. It parses an arbitrary character. So basically just splits the input and gives us the first character and the rest of the string. So what does it do? Well, it has all these parsers have the same shape. It's a parser containing a function which in this case looks at the string. If the string starts with a character C, then it returns that character C and the rest of the string, so just of that. Otherwise, if the input was empty, then it fails. So it only fails when there's nothing to parse. Otherwise, it grabs any character. Let's take the first example of something we actually did see in the examples from earlier. And that was the combinator that combines two parsers by first trying to parse using the first parser. And if you succeed, that's what you get. Otherwise, if you fail, you try and parse with the second parser. So what is it? It's a parser, and the function takes a string and does the following. It first tries to parse using the parser p on the string. Now, what you do next depends on the result of that. So let's do a case analysis on that. If you get nothing, then the outcome is whatever you get by parsing using the second parser on the string. So if the first parser failed, then you try the second parser. Otherwise, if you get something, whatever that thing is, that'll be your result. Okay, before we can start using these to do something interesting, or maybe we've got enough to give one small example. So let's give an example of something which always parses a character. It parses the character it finds, but if there's no character there, then it gives you a default character. Let's say a full stop. So we can build that. We have a parser for an item, and if that parser fails, then we can parse with something that never fails, the success parser, which will find a full stop. So that's a parser that we've built from two parsers we have so far. If we want to try that out, we can parse using that parser on some string. If we give it a string that starts with something, then it succeeds with the first thing in that string. If we give it the empty string, however, it still succeeds, but it succeeds by using the second of those two parsers, namely by giving the plus. Another way of combining parsers is if we first parse with one parser, then we parse with a second parser. We want to parse one thing after another. Now, it turns out that that's not a very general case because the way we parse the second thing may depend on the value that we got from the first. So that's the computation pattern of the next parser combinator, and I've written it as this symbol here. It combines a parser and another parser which depends on an input. In other words, the type, it takes a parser, and that parser produces a value a, of type a, which it feeds into this function in order to then parse a b, and that's the result. The result is the result of this second parsing. So it's a bit like first parse with a parser, then parse with a b parser, and that's the result, except that the way that we parse the b thing might depend on the result we got from the first parser. So this is complex, but actually writing the definition we don't actually have a lot of choice if we keep thinking about the types. So let me fill in the definition. It's the whole thing. If we have a parser here and a function here, then the whole thing will be a parser. And the parser will contain a function which, if you give it a string, it will try first by parsing using the first argument. That's p. So we're going to parse using the parser p on that string. And depending on the result, we do various things. So we're going to do a case analysis on that. So what are the cases of interest? Well, we'll start with the just case. That's the case when we got something. Let's suppose we got a value a, and the rest of the string. So what do we do in that case? Well, we're going to take the value a and we're going to feed it to the function f. That creates a parser for b's. And we're going to run that parser on the rest of the string. So we're going to parse using the parser we get by applying f to a and we're applying that to the rest of the string. And otherwise, if we don't get a just, if it fails, then the whole thing fails. So this is a little bit hairy. This is the only hairy function. In fact, this is the only function we're going to need to define using case expressions. All the rest of the functions actually don't depend on the structure. So we'll get a feel for this function once we start using it in further examples. So the remaining parser functions and combinators and bits and pieces, none of those actually depend on the representation of parsers. So everything we build from now on will be built using the building blocks that we have. But the important thing to note at this point is that now we already have enough in definitions to make parser an instance of the class monad. And the key is that we have two operations, the success, which will be our return operation for our monad. And we have this guy here, which will be our bind operation. This is the type of the bind operation of a monad. It allows us to take a function and apply it to something which doesn't quite have the right type. We need to unwrap the value a from the parser and feed it into this function. And that's exactly what we're doing here. We unwrap the value to get the value a out of the parsed thing and feed it into the function. So if we jump down to the bottom of the file, this is the important part. So this is just a cut and paste. You can cut and paste for any monad definition if you don't want to have to think about functor and applicative. This is the bit this is the creativity. Namely, we've defined return to be success, and we've defined that the bind operation of the monad is just that function we just defined. And in fact, this is what enables us to use do notation. And we'll see how do notation then arises naturally. We'll use this function and see actually how we could instead write it more simply using do notation, or rather more prettily. So let's go back to where we were. We were at the point now of saying we've basically defined everything we need using this constructor P. Everything else we do won't depend on the actual representation. So everything else, and there isn't too many more things. So let's start with the function sat. So what does sat do? Well, you give it a predicate, characters, and it produces a parser for things that satisfy this property. You give it a property P and gives you a parser for characters that satisfy that property. So how do we do that? Well, we can parse an arbitrary item. We can't produce a character unless we can produce at least some character. And then what do we do with that, the character we get from an item? Well, we can feed it using this guy into the function, which takes a character, call it C, and inspects that character. It's going to inspect it by applying the predicate P to C. So we can do a case analysis on that, and it's either going to be true or false. So if it's true, then we're going to succeed with the value C that we found. We've managed to successfully parse a character that satisfies the property we want. Otherwise, we're going to failure, the parser that always fails. So we've built a parser from our building blocks completely independently of the representation of the parser. Now remember that what I said was that this function here in our monads is defined to be the same as the bind operation, okay? But the bind operation, according to the definition of the way bind works, can be written using do notation. And the way we do it, if you consult the definition that we had for that, okay, so here's the notation that we had. If we have an action, some action which is then fed into a function, we can rewrite that to a do in this form. So let's do that with the example we just had. We have an item which is fed into a function. We can rewrite that to a do notation. We would do the following. We run the item parser and call the thing we get from that C. And then the rest of the operation is just the case expression that we have here. So get the value C from the item and then do a case analysis on it and return either this parser or this parser. And both of them are parsers for characters, so they all have the right type. Okay, so now we can move on to define some of the other examples. A digit, so this is a parser that will only parse a digit. And here we use a function from data.char. It's just satisfying the property is digit, which is one of the functions from data.char. So if the character is a digit, then we get a parser. We also used in our example a parser for a specific character C, and that's also easy to write using sat. That's just sat equals to C, where the property we want is that the character we have is exactly C. Okay, let's look at this example, both with and without do notation. So here it is without do notation. It's combining a parser for a lowercase character. So if we parse is ASCII lower ABC, if we parse with sat is ASCII lowercase, then we get the character followed by the rest of the string. If we try to parse something that didn't start with a lowercase character, then we get nothing. So what it does is takes the result of this parse and feed the value that it gets if it succeeds, for example this value, into this parser. And what is this parser? Well, let me write it without the dot notation here, without the higher order sort of style. It takes a character and applies this parser to it. Converts the character into an uppercase character and then tries to find exactly that character. So let's run that on an example with a string which starts with a lowercase and then an uppercase and whatever else. And then it will find the lowercase, the uppercase, which it will return together with the rest of the string. If we modify this to start with an uppercase, it will fail. If we modify it was upper or lower, it will fail. If we have an upper and lower case, but they're not the same letter. Okay, so rewriting this one using do notation, that would be the same as writing do. First run this parser and call the result C, the character C. And after having done that, run the following, char to upper of C. So that would be another way of writing the same thing using do notation. Okay, we've got a few more things to define in our library before we're done. The most complicated one was chain. So let's start with parsing 0 or more things. So this is it takes a parser for a single thing and gives you a parser for a list of things. So it's very similar to 1 or more, except that there might not be any at all. Okay, so how does 0 or more work? Well, we're actually going to define it in terms of its buddy, 1 or more. And 1 or more we're going to define using 0 or more in a mutually recursive way. So 0 or more things is the same as either 1 or more things. But if that fails, if you fail to get 1 or more things, well, you can never fail to get 0 things. You can always succeed returning 0 things, returning a list of things. We can always succeed by returning the empty list if we didn't manage to get 1 or more things. So what about 1 or more? That's maybe a little bit more interesting. Well, here we're going to use do notation. It's a little bit simpler. We're going to parse one thing using P. We'll call that result A. After we've got an A, we're going to get a bunch of A's using 0 or more things. So we get at least one thing. Let me just indent this, maybe it's a bit easier to read. We're going to get at least one thing, and then followed by 0 or more of them. Might be many, might just be none. But whatever we get, then our final result will be return the A followed by the A's. Now remember, return is actually the same as success. So we can use them interchangeably. Return is defined to be success. So it doesn't matter what we write here, but it would be probably more normal to write return in a do notation. Okay, let's define our final building block. I don't think there's any more after this one. And that was the chain function. So this one parses a list of A's which are each separated by B's. So how are we going to do that? That's a little bit more tricky. I'll do a do notation again. I'm going to parse at least one P. I'm going to call that A. So a chain of things, there must be at least one. But then after we found one, we're going to parse 0 or more of something. And what is it? It's 0 or more Q things followed by P things. Q then P. So the way I'm going to write that is using our combining function. Q, I'm going to write a Q combined with whatever result I get from that. I don't actually care what it is. What I'm going to do after that is P. This is just saying parse a Q, then feed the result into this parser. But the result, actually, we don't care. We're not going to use it. So it's like parse a Q, throw it away, and then parse a P. And we're going to do that 0 or more times. So we're going to get a whole list of the things that P returns, a list of A's from that. We've got a single A. We're going to get a list of A's from this guy. And then the final thing we do is put them together. Now, remember that this function here is the same as the bind operation. And in fact, whenever you do bind this thing and a don't care function here, there's in fact another function in the monad that represents exactly that pattern of computation, and that's written as just double arrow. So it says perform this action, ignore the result, and then do this action. And that's exactly what we want to do in the chain. We want a chain of expressions separated by the plus character. We have to parse the plus characters, but we don't keep them, we throw them away. We're only interested in the expressions. Yeah, I spelled something wrong there, 0 or more. Okay, let's take a little example. Comma separated digits. We're going to parse a comma separated digits. So we're going to parse using a chain of digits separated by commas, and the comma is char, the comma character, so that will parse a comma, and then we can parse that on a string of digits, 1, 2, 3, 4, and then maybe some other junk at the end. And then we get a string of all the digits. We've parsed the commas in between them, but we've discarded them because that's what the chain parser does. Okay, so that's the whole of the library, and the fact that it's made an instance of a monad by using some boilerplate standard stuff, but most importantly is identifying what the bind operation is and the return operation are of the monad, because that's all that's needed to write down do notation.